Hello everyone, and welcome back to another video, and this is probably my favorite integral I've ever done on this channel. It took me a little while to do, but it's absolutely awesome, and even though I should be studying for my chemistry test, this is just too awesome to ignore. So, let's just jump right into it, shall we? The first thing we're going to do is basically apply Feynman's technique. So, I'm just going to basically let f of t be equal to the integral from 0 to 1 of the natural log of 1 minus x over x to the t dx. I'm defining it like this just so we avoid differentiating with respect to n times, because that gets really messy. So basically what we're going to do here with this is find we're going to differentiate this with respect to t n times this function of f. So integral from 0 to 1. And what we're going to actually be differentiating is not this natural log term, but this 1 minus x over x to the t here, dx. And this is just because whenever I'll write this off to the side, whenever we are going to differentiate, I'll just do it like once. Whenever we differentiate this with respect to t, this 1 minus x over x to the t, well, this right here is just constant relative to the t. So what we end up getting is just a 1 minus x over x to the t, but then times a natural log of 1 minus x over x. So if we differentiate it n times, basically what we get is multiple powers of that right there, as this right here does not actually depend on t. So that's kind of the rationale behind this choice right here. And actually looking at this integral, it looks pretty bad, but if we actually write it in a slightly different form, I'm going to be omitting the derivative symbol just for now, for the sake of brevity. If we actually take a look at this integral right here, I'm going to write it in a slightly different way. We have a 1 minus x to the t. Oh, sorry, I did forget to mention. The derivative here is going to be evaluated at t equals 0, as we do want this term right here to go not go to 0, actually, put a number here. I'll go to 1. So, apologies there. Well, I'm just going to be omitting the derivative symbol for a little bit. So if we just rewrite this in a slightly different way, what we find is that this is our integral right here, which looks a lot like the beta function, because it really just is. This right here is just equal to beta of 1 plus t comma 1 minus t. And we can simplify that, or evaluate it, by saying, okay, well, we know what we can evaluate beta in terms of the gamma function, of course. So what we have then is gamma of gamma of 1 plus t times gamma of 1 minus t over, what we end up getting is like gamma of 2, because you end up adding those two things together, but gamma of 2 is just 1, so I'm just going to kind of erase that. So that's what we're left with there, which doesn't look very nice, because remember, we do still have to differentiate this with respect to t, not just once or twice, but n times. So finding the derivative of that might seem like a pain. But we can exploit one more thing we know. We can exploit Euler's reflection identity, I believe it's called. And that's basically the fact that if we have gamma of, say, x times gamma of 1 minus x, this right here is just equal to pi over the sine of pi x. And based on this, you can see a lot of parallels. The only thing that's different is that, well, we have a 1 there, but based off of the property that gamma of x times x is equal to gamma of x plus 1, well, if we just kind of multiply both sides by x here, these two things are now entirely equivalent. So we can now rewrite this as just pi times, well, t instead of x over the sine of pi times t. And this is where I originally got stumped, because that in and of itself is a very nice result. Yet that's not really what we get, because we actually have to apply the derivative here. So we have to differentiate with respect to t n times in this scenario, and then evaluate it at 0, of course, but that's implied at this point. we have to evaluate this nth derivative, which really does not look very nice, yet it is doable, and the result is absolutely amazing in my opinion. So the way we're actually going to do this is just have we have another note on the side. We have a lot of notes this time. But just one good thing to note is that cosecant of x, one way we can express this actually, and here's where some complex numbers come in, but don't worry, I promise, they go away. It's all in your imagination. No, I'm kidding. Well, maybe it is. Inception. Anyways, we can express cosecant of x in terms of a power series, and this is just equal to negative 2i times the sum from k equals 1 to infinity of e to the xi times 2k minus 1. And that right there is just the expression for cosecant in terms of a complex exponential. It just looks really ugly. But the reason why we would want to do this is because you'll notice here that we have a t here and an e there. So let me just kind of write this out, and then I'll kind of explain the rationale for doing something like this. So what we end up getting, I'll stick with the blue, it's kind of nice. So what we end up getting is I'll pull all of the constants out. So a negative 2 pi I, I'm writing it in that order because, you know, complex analysis. Anyways, k equals 1 to infinity of t times e to the 2k minus 1 times pi it. Oh yeah. It would help if I did do the derivative here. Sorry. A lot of moving parts here. But yes, that's what that's equal to. And the whole rationale for actually writing out this in such a way is so that we can look at this right here, because that's a constant, we don't care about it. We can just throw the derivative inside the summation, meaning that we're just differentiating, essentially in form, something along the lines of x e to the ax, but we're differentiating that not just once or twice, but n times. And what I did in my last video, and this is, I didn't want to prove this in this video, I wanted it to be a little bit shorter, that's why I did a separate video. That's called a plug. But anyways, but we know from the last video that the nth derivative here is nothing but a to the n minus 1 times e to the ax, but then times ax plus n. And we can just apply that here, really. It's not going to be pretty, but it's really not all too bad. And again, I just kind of want to emphasize the whole rationale for writing it like this is so that we can exploit this identity right here and actually take the nth derivative. Without this, it might be possible another way, but this is just kind of the most straightforward way I've found. The only straightforward way I've found, if you can call this straightforward at all. Anyways, so we're just going to be applying this right here, and I'll zoom out a little bit to keep all that on screen, but I'll switch to kind of this. I'll stick to the blue, actually. I won't. What we end up getting is, well, we still have our negative 2 pi I out front, and I'll write our summation here. But we end up getting is that our A is just equal to our 2k minus 1 times our pi I. So just subbing that in, what we end up getting is 2k minus 1 pi I, and then to the what is it, n minus 1 times e to the ax. I'm writing it like that for a specific reason, don't worry. Times ax plus n. And I'm keeping that in terms of a because we do have to remember this is being evaluated at at x equals 0, because you'll remember up here, if I kind of scroll up a little bit, is that we want this term right here to go to 0. We just want this natural log bit, and because of that we need to evaluate the derivative at 0, meaning that if x is 0, then I'll write this in red. Crossing stuff in red is always satisfying. That's 1. Simplifying our entire expression to just negative 2 pi I times 2k minus 1 times pi I to the n minus 1. I'll simplify the pi i's here in like one moment. Times n. And oh, and it would help. And yes, there is a summation here. Sorry, meant to write that. So let's just kind of simplify this one last time before we really start to dive into this summation bit right here. So what we have is a -2, and then we have an n. I'll put the pi in between the n's. We have a -2 pi, or actually I won't. Apologies. And then we have our sum, 2k minus 1 to the n minus 1. And then we have just this pi I term raised to the n power. Because you have a pi I here, a pi I there, it all simplifies quite nicely. So I'll actually, -2n, you can come on and join the rest of the pack. So yes, that right there is what we're left with. And now all we have to do is evaluate, from k equals 1 to infinity, of course. Now all we have to do is evaluate this bit right here, which might seem a bit daunting, but let's actually consider what this is saying. So this right here has a lot of resemblance to the zeta function. So another tangent. So we know that the Riemann zeta function, I apologize for the zetas throughout this video. We know that zeta of some s, that's actually a nice pink color, I've never used that before. Some zeta of s is equal to the sum from k equals 1 to infinity. I'm going to stop writing the bounds for the summations now. It's going to be an implied 1 to infinity from now on. This is, or I'm going to write this zeta of negative s actually. This is just equal to, oh, meant to erase that. This is just equal to k to the s, right there. And we can write this in almost, we can split this up in a way. Because we can, what we're essentially doing is saying this is 1 to the s, plus 2 to the s, plus 3 to the s, plus 4 to the s. And what we can kind of say is, well, what if we like grouped the odds and evens together? Which might sound absurd at first, but if you actually look at what we're doing here, is that we're only summing over the odd numbers. Meaning that if we can subtract, say, some of the even numbers from our zeta function, we can simplify it a bit. So let's try to do that, shall we? We can say that this is the same thing then as the sum over all even numbers. So that'd be 2k to the s, and then plus the sum over all odd numbers, which is just 2k minus 1 to the s. And based off of this, I mean, all we have to do is, just off of this, is just subtract that from both sides. So this just tells us that our sum of 2k plus 1, or sorry, 2k minus 1, excuse me, 2k minus 1 to the s is just equal to the sum of k to the s minus 2k, and that's all to the s. But, I mean, we can just factor out a k to the s here, right? And then we can just put that in terms of the zeta function. So this right here is really just the sum of 1 minus 2 to the s, and then k to the s. Meaning that this right here is just equal to 1 minus 2 to the s times zeta of, well, negative s. And this is what we've just evaluated our infinite series in terms of the zeta function, which, I mean, is awfully helpful by virtue of, well, we just have our series right there. So I'm going to just sub that in real quick. I'm going to change to a different, oh, I can use that a gold color, I guess? Or I can stick to the blue. Nah, it's good gold. Or gold yellow, I don't know. I'm going to call it gold, because gold's nice. Okay, 2n to the pi I to the n. Then times our 1 minus 2 to the s times zeta of negative s. But let's kind of ask ourselves here, what actually is our s? So, I mean, it really isn't that hard to, it's not that hard to figure out. I mean, if we have our 2k minus 1 to the s here. We have 2k minus 1 to n minus 1. S is just equal to n minus 1 here. So really what we have is, I'm just going to erase this. All we have here is an n minus 1. And then what we have here is just a negative n minus 1. So it's going to be 1 minus n. Yet, there is one thing I haven't really mentioned. And, well, I suppose two things, but they're really connected. You'll notice that we have an I here, and that kind of throws a wrench in things, because you'll say, well, if we plug in a number, say like an odd number, say like 3 or 5, and we're going to get an imaginary number for our slope, which really does not help us at all whatsoever. And I think, I mean, at least in my mind, the way I interpret that is that the slope there is not going to be really defined, and that something went wrong along the way. And so the point is there, essentially, that this is only going to work for even numbers, this n. And also, if you just evaluate the integral and say Desmos or something, you'll notice that for n odd, our integral is just equal to 0. That just holds for all odd numbers. So basically what we're going to do is we're going to take this little formula here and basically only apply it for even numbers. So we're just going to say that n is going to become, say, 2n. And for this, on my own sake, so I'm not saying n so many times, I'm going to say m, because yes. So, n equals 2m. So what we have here then is this is just equal to negative 4m times pi I to the 2m times 1 minus 2 to the 2m minus 1 times zeta of 1 minus 2m. And this right here is essentially our answer. We just need to kind of clean it up a bit. And the way we're going to do that is kind of take a look at this I term. So we have an I to the 2m times negative 1, because that right there. So, but this is just equal, well, I squared is negative 1, so we have a negative 1 to the m, but then we're being multiplied by negative 1, so we're just going to say this is negative 1 to the m, and then plus or minus 1. I'm going to go with minus. Or, well, you'll say plus, I suppose. So, well, we've really simplified this a lot, haven't we? This right here is just equal to 4m times pi to the 2m times negative 1 to the m plus 1 times 1 minus 2 to the 2m minus 1 times, oh, I cannot draw zetas. Goodness gracious me. Times zeta. There we go. Times zeta of 1 minus 2m. And that right there, ladies and gentlemen, is our answer to the integral. That is our solution. So we've tackled a lot in this video. We've done a nasty integral, but also we found the nth derivative of x over like cosecant, or sorry, x cosecant, and some pi's thrown in there. So yeah, I hope all y'all enjoyed this video. Thank you for watching if you made it this far the way through. Oh yes, I actually did remember, I do want to do a bit of a reflection here. It's a 19-minute video. If anyone makes it this far, I'll actually be kind of surprised. Anyway, 19 minutes 20, what's the difference? So the whole idea here is actually, this is inspired by Maths 505 integral, where this was originally, say, a 1 minus x over x plus 1 at the bottom. That's what it was originally. But then while trying to evaluate that, I got here with the beta function. Yeah, I got, or I didn't get here with the beta function. I got here, but instead of that being an x, it was like a 1 plus x. And I thought, well, wouldn't that be awfully nice if it were, say, an x instead of a 1 plus x? So I basically just kind of changed the problem. Because I thought it'd be interesting to just kind of investigate, and then it kind of spiraled. I'm like, well, hold on, you can do this and this. You can apply the beta function, and then you apply Euler identity, and then you apply the series, and you get that. So anyways, just a little kind of I won't say reflection, but just kind of inspiration, rationale, I suppose, of where all this came from. So yeah. Anyways, I hope y'all enjoyed this. Made it through this 20-minute video. Hope y'all enjoyed, and I'll see y'all in the next one. Adios.